distance. I may have to cut it short at the end. I have to put this in my pocket carefully without turning it off. Here we go. Okay, welcome back everybody. Here we are beginning the lecture sequence now for Geography 128. And in light of the fact that as we did our quick poll of everybody that's in the class last time, at the beginning of the sequence of the class, what I'll do is repeat some of the material that those of you that took Geography 176A or Geography 12 should probably be familiar with. That's the concepts of geodesy and scale that I'll go over today. That is, how do we create an Earth model that we're going to use to transform to become a cartographic model? And then how do we transform that from the size of the Earth itself, 40 million meters around, so that it's the size of the window that we have open on the computer at a particular time. Then I'm going to spend a lecture on map projections. Since we're doing a first assignment on map projections, it's probably a good time to do it. And then I'll spend one lecture on coordinate systems. And with that, I've covered enough basic cartography that we can move into the computer cartography aspect of the class. Okay, so if what I'm going to say is familiar to you, my apologies. If you're coming straight off of having done 12 and 176A in the first last quarter, you're going to be a little bored, but hey, it never hurts to do a refresher, does it? Okay, first I have to get used to the snail's pace at which this projector works. There we go. So I often introduce cartographic transformations by saying that we can talk about any kind of input, and that can go through some kind of transformation, let's call it T, and that gives us some kind of output. We can put boxes around these and make this nice simple diagram. Couldn't be simpler. This diagram goes back 50 years in terms of data processing, or precursor to computer science. In almost every case in cartography, we're dealing with an input being some kind of geographical data, in other words, locations on the surface of the Earth. The transformation being something that substantially modifies either the coordinates themselves or the content of the data, and the output being often some kind of rendering, or at least the same data but in some kind of different format. And when we produce a map, we actually have to go through this loop several times to be able to get to what it is that we want. So I often say we can talk about two fundamental transformations, and they're the very first two that we have to deal with. Let's call them T1 and T2. So the T1 is the fundamental transformation of going from the entire Earth and measurements about the entire Earth onto a globe. Okay, that's a fundamental, very important transformation. We begin with observations about the Earth. Imagine somebody out there, say with a GPS receiver, measuring a coastline or a ship reporting its position. And when we transform it, we end up with a position on a three-dimensional object, a globe. How big the globe is depends upon the next transformation that we're going to go through. Okay, so the first thing that's going to need to happen is a fundamental change of the scale at which we're operating. Okay. The entire Earth, it's kind of big, 40 million meters around. Generally speaking, when we're dealing with a map, they're usually less than a meter on a side, so we've at least changed it by a scale of the order of millions down to come up with what we want. This fraction, the fraction that we use for the transformation, we call it the representative fraction, and it's a very important fraction in cartography. Okay, so we often express it like this. There's a ratio with a 1 on the left and then a colon and then a number on the right, and that's exactly the same as putting a slash and making that a fraction literally. That factor we often call S. The actual value itself we call S, as we'll see when we look at map projections. Now, an important thing that happens, and I actually call this a new transformation in my most recent work, is that when we transform from the real Earth to the globe, we have to make a set of decisions about how we're going to symbolize on the globe. In other words, let's say we can transform the coastlines and they map onto a series of black lines on the globe. We transform the oceans and they map onto a set of regions on the globe that we decide to color in blue or cyan. Well, it's a symbolization decision. You go and look at the ocean today, it doesn't look very cyan, trust me. It looks pretty like grey today with breakers on it. So we make a choice about how we're going to symbolize it. We start with something real, a real thing in the real world, and we end up with a symbol that's going to represent that thing. A road which has properties like, you know, the depth of the tarmac, the width of the highway, the number of cars driving along it, the pattern of the white line and the lanes painted on it, is going to become simply, let's say, a red line with black edges on our map. That's what I mean by the symbolization transformation. Now, one thing we have to do when we go to this first transformation is that we need to choose an Earth model. An Earth model simply means what shape are we going to take the entire Earth and map it onto, so that we can then go through the next transformation, the projection transformation. Now, when we go to a globe, the kind of globe you might buy in the bookstore, we make this assumption that we're going to map the Earth onto a sphere. And that's not a bad assumption, as we'll see in a few minutes, but it's not sufficiently accurate for all purposes as far as mapping is concerned. We don't have to go very far on the Earth's surface for the details of the Earth's curvature to come into play and to begin to distort things. That's why geodesy becomes an important factor. Okay, so we need to choose an Earth model, and I've put in parentheses here the word datum. Datum is the key, because the mapping of the actual Earth's surface onto our model assumes a datum. And the datum is now going to carry along with our data. If we don't take it into account, we're going to make some serious mistakes. All right, so that's the first transformation. We start with the whole Earth, we end up with a globe. And there's some real advantages to a globe over the entire Earth. You know, I can make quick decisions just by looking at it about what the best route between, say, San Francisco and Tokyo is. Just by looking at it. I can hold it up and make decisions about the proportion between the Earth and the water on the globe without too much trouble. Next, we have the problem that when we have a globe, if I hold it up and look at it, I can only, on the best day, I can only see half of it. Actually, I usually see a little bit less than half of it, because I'm seeing it in perspective. What I would like to do is take the entire surface of the globe and somehow squash it out flat and put it onto a single representation called a map. Okay? So on that representation, we might be able to see the entire surface of the Earth all at the same time, even though I could never do that as a human being. I can never do it from space in a spaceship. I can never do it from the moon. It's a composite view. It's a composition that we put together to represent the Earth. This involves going through a map projection transformation. This is what we're doing in the very first assignment. The bottom line, if you had to summarize the projection lecture, which is coming up next week, is that we can't do any kind of map projection transformation without inherently distorting the map in a huge number of different ways. And we'll go over some of those ways in the lecture. So it's inherent. You might say that all maps are lies. They're all distortions of the true Earth. Only the Earth itself is a true representation of itself. All right, so that's by means of introduction. Before I get technical, let's start with Earth models. So as I said, the first thing we need to do if we're going to map the Earth is to say we're going to take some symbolic form onto which we're going to assume that the Earth resides, and then we're going to take that form, shrink it, and flatten it out. Well, the forms that have been used over the time varied substantially. It's been argued that the plane was the first model, and in fact, if we're only going to map a very small area, the plane is a pretty good model of the Earth. If we were going to make a map of the desks in this room and the layout of the room, we could begin with the assumption that the floor of this room was flat. Not a bad assumption. We could make a pretty simple map by making a few easy measurements. But the bigger the area we take into account, the less we can disregard the fact that the Earth is not flat. It's been said, and I once tried to prove this when I was visiting, that some of the buildings in Washington, D.C., in particular the headquarters of the Department of Agriculture, the corridors within the buildings are so long that if you put your head down on the floor and look along the length of the floor of the corridor, you can actually see the Earth curving or dipping away at the far side. Okay, so a single building, and certainly something like a bridge or a highway, if we don't take into account the curvature of the Earth, we're going to be in for some serious engineering problems, let alone cartographic problems in representing things like continents and countries and so on. Okay, so the plane is at a disadvantage. Other models of the Earth that have been used include the sphere, which is not a bad representation. In fact, most map projections assume the sphere because the math is so much simpler. The ellipsoid, and we'll meet that in just a second, which is simply an ellipse rotated in 3 dimensions about its shorter axis. And then the more complex geoid, and I'll finish by talking about the geoid today, because as we get better and better at mapping, we're beginning to realize that even our best ellipsoids sometimes are not adequate for very, very detailed mapping purposes. And we need to go on to sort of what I call extreme mapping, which is to use the geoid, where we need to snap everything to a very much to its local detail. Okay? In much of the world, as I said, for many mapping purposes, we can simply assume the world is flat. But it doesn't take long before we realize that that's a problem. When the Public Land Survey System was started in the United States, they simply rolled out to Ohio, hammered a stake in the ground, and said, we're going to draw a line dead straight north, we're going to draw a line dead straight west, and then we're going to start laying out squares on that grid, 1 square mile of each, and just keep going. Well, as the Hutchins was the first U.S. geographer, that's still an office in the Secretary of State's office, wrote back to Thomas Jefferson very quickly and said, sorry, I don't get very far before something's going wrong here, that the Earth is not flat and I need to take it into account. So we need to work out corrections, and the corrections get very ugly very quickly, so it's much better to work on a 3-dimensional form. Now, there are lots of myths about the Earth being round. The sphere has indeed been assumed since the times of Pythagoras, so in spite of what you hear about the Flat Earth Society and so on, humans have believed that the Earth is indeed round for a very long time, thousands of years. And indeed, Aristotle himself introduced a series of what he called logical proofs for the curvature of the Earth. They were mostly thought experiments at the time, but they can be very easily repeated. The ellipsoid has been used since it was discovered that if you assume the map is a sphere and actually start measuring distances, north-south versus east-west, you start coming up with different lengths. And to get rid of that discrepancy, it was decided that we had to make a series of measurements that I'll describe in a minute that result in the shape changing, the actual shape that we're using changing. It's not an enormous change, it's about 1 part in 294, but it's significant enough that in large-scale maps and certainly in many small-scale maps, it does come into account. And then the geoid is kind of like a crazy technology story run amok. We keep getting better and better and better at describing the Earth's exact shape with geoids. The most recent ones use something called spherical harmonics, in which they account for every property and sub-property of the Earth's shape up to now, I think, like 49,000 harmonics or something like that, which is probably way too much detail. What does this mean practically? You may or may not have flown over the country, looked down and wondered why there are all these little green squares down there on the surface of the Earth. Well, those are laid out on the field boundaries. So farmers bought fields, or their ancestors bought fields, and those fields, generally speaking, were a section or a part of land, and that was square. It was 1 square mile on the side. And those are laid out according to the Township and Range Survey System. The Township and Range Survey System had subsections for every 6 miles east-west, latitude and longitude in the field. But every time they started measuring these out, and using surveying instruments to measure them out, using stellar observation to correct their latitude and longitude at the corners, they realized that something was going wrong. So we end up with what are called corrections. Okay, so here we are, we're pretty far out. We're at 3 north, I think that's, I can't read that was 5 east. So we're only 5 east of the principal meridian in the survey system, and now we've got to correct for the curvature of the Earth. And we do that by offsetting one system against another. We have to put in all these compensations for making things flat. Here's another offset. By now we've got adjacent areas that would be lined up if the Earth was perfectly flat, coming several, more than a mile apart. Okay, back to Aristotle, who lived a little while ago. These are the arguments he made for a spherical Earth, and you can repeat every one of these should you so choose. every portion of the Earth tends towards the center up until by compression and convergence they form a sphere. That's his exact quote. He observes that travelers going south see the southern constellations rise higher above the horizon. In fact, there's a set of stars that if you observe from a single point on the Earth's surface, you observe the stars over an entire year, there's a set of stars that at some time of the year dip below the horizon. You just can't see them. And then they come back again. Observing those stars is the way we can tell time and the seasons and so on. But if we get a different set of stars, we go further and further south, we see stars that we didn't see beforehand. Obviously, things are very different. Anybody who's been to the southern hemisphere here? That's way too few. What are you doing, guys? Come on, get on a plane. Travel more. Southern hemisphere, they often talk about the famous Southern Cross. Entire constellation you can't see in the northern hemisphere. Okay, so take it from me, the world is indeed different. And then this idea of shadows, that during a lunar eclipse, we actually see the shadow of the Earth being cast onto the moon. So it's like seeing a little picture of the Earth. It's only 2D because we're seeing it flat. But it is a curved shadow. So the fact that the Earth is curved implies this sphericity. We can, of course, also prove it by direct observation. A person that's about my height, my level of eyeballs, if I was able to, let's say, stand on the ocean, in the middle of the ocean, like on one of those paddle boards, for example, I could only see until my eyesight disappears, or my level of view disappears over the horizon. I can only see about 5 kilometers because the Earth is so curved that my line of sight disappears very quickly. So what does this mean? The distance is greater than 5 kilometers, certainly more than my height, in the order of several meters. So here's a ship. This is actually off the coastline, the east coast, off of Delaware. And we have a ship going by, a container vessel, and it's, let me guess the distance, let's say it's 20 miles off the coast. I can still see it because it's still visible. The air is very clear. But where's the hull? Okay, anybody that's seen a container ship knows that they usually have something below the freight. Okay, I can't see it because it's beyond the curvature of the Earth. Okay, so I don't have to go more than 20 miles to need to take into account this curved shape of the Earth's surface. Well, those of you that have taken more than one class with me know that I always love to insert history into my classes. So let's do a little bit of a historical investigation. When it was realized that wasn't not only curved, but the curvature varied depending upon where you measured it, this became one of the classic experiments in scientific history. We're talking in the mid-1700s here, right after the French Academy of Sciences had just been founded. One of the things they wanted to do was to figure out how big the Earth was, how much it weighed, very simple kinds of arguments. How big was an important question. So they started measuring the size of France. They did it by triangulation. They measured from one tower to another with telescopes, forming series of triangles. If they knew the length of one side of the triangles, they could solve the other triangles if they knew the angles. And they expanded this network of triangles from an area originally near Paris out to extend to cover the entire land of France. Also, it started in the Netherlands, but ended up in France. Then the Cassinis, the famous mapping family that mapped France, decided that they would have a prime meridian, that they would draw a line through Paris, on which they were going to build the Paris, the French Academy of Sciences Observatory, and they were going to take that line from the northern coast, where it met pretty much near the small town of Dunkirk, all the way down across France to the Mediterranean, where it met the sea at a place very near a city called Perpignan in southern France. Now, to measure that length of arc, it took years, many, many years. In fact, 3 generations of the Cassini family extended that line bit by bit. And as they started measuring that line, they realized that 1 degree of latitude near Paris was not the same ground length as 1 degree of latitude near Perpignan. That the distances were different. They didn't know exactly why this was happening, so they proposed a grand experiment. They said if these are different on the Earth's surface, if we sent an expedition up to a very high latitude and measured the length of a degree, and we sent another one to the equator and measured the length of a degree, we'd be able to prove the exact shape of the Earth. In fact, they had an idea about the actual shape. They thought it was an ellipsoid, but they didn't know whether it was oblate or prolate. What exactly does that mean? Here's an oblate ellipsoid. It's an ellipse with the longer axis running this way. Okay, a prolate ellipsoid is one with the longer axis running this way. I call these eggs and these pumpkins in my latest book. Okay, so all we had to do was go out and measure 1 degree of latitude here and 1 degree of latitude here, and would be able to determine the shape of the Earth, whether it was oblate or prolate. Well, to cut a long story short, 2 expeditions were sent out. The first one was the one that went to the high latitudes. It went to present-day Lapland in present-day Finland, up here on Lake Tornio off the Gulf of Bothnia, and there they measured a degree of just slightly less actually than a degree. They had to figure out all sorts of things like how do you lay out a baseline on a frozen river, and how do you climb mountains and in the snow and those sorts of things. But eventually they reported back. The leader of this expedition was a guy called Maupertuis, and he reported back to the French Academy of Sciences after about 3 years the distance of the measurement. Well, the other group didn't have it quite so lucky. They decided to go to Peru, in fact an area that's now called Ecuador, equator, get it? That was sectioned out from Peru later. Unfortunately, the 2 principals, Le Condamine, Gaudin and Bouguer, the principals in the expedition, Gaudin was the nominal leader of the expedition, had a terrible fight on the way out from France. Such that they weren't even talking to each other by the time they arrived. They went through there was no Panama Canal, so they had to cross the Panama Isthmus and go down to Peru. By the time they actually started work, they just decided to do completely separate measurements without talking to each other, in fact without having contact with each other. The first of them back was Bouguer. He went back and reported his result by sailing backwards to France. Le Condamine decided that he would do something different and go back down the length of the Amazon River to get back to France, which only took him a year or so. And Gaudin actually got so totally involved and was accused of murder at one point and married a local woman. He didn't get back to France for another 8 years, at which point he'd been stripped of his membership of the French Academy. But that's a long story. Anyway, they ended up measuring 3 degrees of arc. They were very upset to know that they'd been beaten to their measurements by the other group. But when they put the numbers together, it proved, and with the Cassini numbers for France, it proved quite conclusively that just as Isaac Newton had suggested, the Earth was an oblate ellipsoid and not a prolate ellipsoid. Okay. That was the first of the measurements. They've been repeated ever since. In fact, there are something like 39 or 40 different repeat measurements now of these distances, which bear this out. Now, it's not a simple measurement, simply because the problem with these measurements is that when we measure latitude, in fact, when we say latitude, we think we mean latitude here at the center of the Earth. But in fact, we don't. We actually simply usually assume that wherever we're standing in the world, if we hold a plumb bob on a line, that it's pointing directly down, okay, to the center of the Earth. Well, it is indeed pointing directly down, but it's not necessarily pointing to the center of the Earth. It's pointing to the center of mass of everything that's beneath you. Okay? So you can imagine if you're actually on the equator itself, yes, indeed, your plumb bob's pointing to the center of the Earth. If you're actually standing on the North Pole, your plumb bob is indeed pointing to the center of the Earth, but since we've got a non-spherical Earth, anywhere else it's going to be pointing to somewhere that's not at the center of the Earth. So we have this difference between geodetic latitude and geometric latitude as far as the Earth is concerned. And the lengths can be significant. So here's the length of 1 degree of latitude. At the equator, it's 110,574 meters. By the time we're up near the pole, it says 90, but that must be, say, 89 to 90. We're at 111,693.92 meters, and this is a significant difference. It's enough that we have to take it into account when we're making maps of the landscape. Incidentally, the other thing that the French were doing was trying to come up with a new measurement of the distance between the equator and the North Pole. That was going to be the longest arc ever measured on the Earth's surface, which indeed it was. At the time of the French Revolution, when they decided to create a new measure of length, they decided that the best way to do it was to take the longest thing ever measured and divide it up. They took the longest thing ever measured, the distance between the equator and the North Pole on the meridian passing through Paris. They decided to divide it by the number 10 million, and they called the result a meter. Okay? So a meter is quite convenient. In fact, if we take that's because that's 10 million is 1/4 of the way around the world, so 40 million meters is all the way around. If we take that and divide it by 360 and get degrees, we end up with 111,111, very close to these numbers. Okay? So if anybody sort of rattles off distances to you that don't make sense, I've traveled thousands and thousands of miles and so on, just do a little quick mental check against the actual size of the Earth. Okay. Now, I don't want to dwell on this issue too much. I'll point out what the implications of a datum in the Earth's model and the Earth's shape are for mapping directly. But it has all sorts of consequences. Okay? One that I don't talk about in my other classes that I like to talk about here a little bit is that we always assume that we can measure anything from the Earth's rotation axis, right? And we choose that. Why? Because it's stable. It doesn't change. Oh, yes, it does. It does change. Okay? If you repeatedly measure the actual location of the North Pole, it wobbles. Okay? How much it's wobbled over Earth history, who knows? Perhaps even the Earth's entire flip from one end to the other over time. We've certainly reversed magnetic polarity in the Earth some 17 or 18 times. Maybe the axis of rotation has changed. So this little map here that says 0 here, here, and 0 here. So this is the actual location of the true pole, would be here. But you'll notice that over time, the location of the pole varies. Okay? So if we're going to set a datum, an Earth model, we have to put a date on when we measured the pole. Okay? Because the pole moves. So if you go down here to the red, these are measurements of the Earth's axis of rotation in the 1980s. So this is the first one. It would be in 1980. And look at what happened to the North Pole over time. And then it went into big circles, and then it came back into smaller circles. Weird, huh? It's been suggested that even building large dams on Earth, in other words, keeping water higher above the center of gravity of the Earth than it normally would be, is sufficient to change the scope of this wobble, just in case you doubt that humans can change the Earth. Okay, another aspect, since we're still in the world of geodesy, is the idea of weight and mass and how that changes. So if we can talk about the geometric center of the Earth, but is that also the center of mass of the Earth? Well, we know that the interior of the Earth is liquid, and it's very fluid. We know that all sorts of stuff happens as we go up towards the mantle, and we have different thicknesses and densities of material. Material that's older is often denser than material that's newer, for example. This wasn't even realized until the late 1700s, early 1800s, during this period of work on what's called the attraction of mountains. And much of this is coincident with some of the earlier Academy of Science stuff that I talked about earlier. So the paper on this was called The Attraction of Mountains. When I think of the attraction of mountains, I don't think about measuring them, but this was the title. And they chose this place, Schwachelian in Scotland, simply because it looks so nice and symmetrical. You know, it looks kind of like Kilimanjaro or something. It's beautifully symmetrical and even. So here it is, Schwachelian, that's how you spell it, and it's in Scotland. So the actual experiment to estimate the mass of the Earth dates from 1774, just 2 years before the American Revolution. The isolated position of Schiehallion, it's separate from other surrounding mountains, and its regular shape, the fact that it's symmetrical, led it to be selected by this guy Charles Mason to do this experiment on gravitation. Now, you probably heard of the Mason-Dixon line. Mason was the guy who came out to America to survey that line, which incidentally, while it was designed to measure the boundary between Maryland and Pennsylvania, before they even started that, they conveniently measured a line down the Delaware Peninsula, Delmarva Peninsula, that actually is still part of a state boundary, but they measured that because they wanted to repeat the measurement of 1 degree of longitude on the American continent. So they used a simple method, deflection of the pendulum. So they basically measured a down vector, and if you do it from a swinging pendulum and time the period of the pendulum for different length periods and so on, you can make a pretty good estimate of the force of gravity. Now, you probably heard in high school that G, the universal force of gravity, was 9.81 newtons, or if you are of my daughter's ilk, it was probably rounded up to 10, which is, I don't know why they started doing that. But in fact, it's not a constant, it's a variable. You know, we always think that things in science are constants. Here's another constant that I'm now telling you is a variable. So G is not a constant. The initial measurements were made by the Astronomer Royal. His name was Neville Maskelyne, and he and Isaac Newton had a long time battle over the publication of some of his observational results that ended up in the selection of Greenwich as the prime meridian. When they finished, they'd made a total hash of all the measurements. So they took all the numbers and all the logs and everything and gave them to this poor guy, Charles Hutton, who had to spend years devising a way to correct all the data and come up with the answers. He developed a graphic system to represent heights on the mountain that later became known as contour lines and became adopted and used elsewhere. So what is the deflection of the vertical? What is the attraction of mountains? If I set up and measure gravity on this side of the mountain compared to this side of the mountain, on this side of the mountain my attraction should be this way, towards the center of the mountain. Well, the plumb bob is being attracted towards the larger mass, so I end up with a measurement towards the Earth's center, so-called center of this one, and vice versa on the other side. So the experiment was actually to set up 4 stations, north, south, east, west of the mountain itself, measure the exact down vector on each of those points, and they concluded from this not only what the mass of the mountain was, Newton himself worked on those data, they also concluded what the force of gravity was and how it varied geographically over space. They also noted that the down vector, the actual vertical, wasn't pointing to the center of the Earth, so we needed to make some corrections for that as far as mapping was concerned. The important implication for the Earth on the ellipsoid then is that when we're at the North Pole, we're actually closer to the center of the Earth. So if you know about the actual force of gravity, it's the product of 2 masses times the inverse square of the distance between 2 masses. So we're going to have a stronger pull of gravity at the pole than we are at the equator, leaving out the rotational forces now entirely. Okay, so gravity, again, is non-constant just because we're now assuming that the Earth is an oblate ellipsoid, not a sphere. Okay, when we actually map gravity, and yeah, questions?
If you stepped on a scale, like on the equator or on the North Pole, is there enough difference to actually see that?
If it was an accurate enough scale, yes. See, if you want to...
What would it be on, like, the first, like, 0.1?
Order of magnitude, I couldn't tell you, but give me 5 minutes in the back of an envelope, I could probably give you an approximation. I'm not advocating that you actually go up there just before your next medical exam or anything and try it. But certainly if we took a scale to the moon and measured ourselves there, we'd certainly have a different result. Okay, so we actually have now instruments called gravimeters, digital instruments that basically set up a little coil that measure the force of gravity on a little particle. And we can take these around and measure the force of gravity And it turns out that it's way more complex than we thought. So if we talk about what's called an equipotential surface, and that is given the form and the gravitational direction of down at every point in the Earth's surface, we can start to talk about an actual form of the Earth that's different from our reference ellipsoid. Okay? Now when we do that, we usually we assume that we begin with the perfect ellipsoid and we measure differences from it. So this is a geoid called Geoid 03. It's one of the more recent ones. There's actually one called Geoid 12 now, which is quite up to date. But in this case, we've got differences in height between our elevations on WGS 84, that's an ellipsoid I'll introduce in just a second, and the actual height on the ground. Okay, so here we are, we're just showing North America. You recognize, of course, North America. We're about here. Here we go from negative 50 in this in the ocean here to about 0. So in other words, most of our part of the world is below the height that you would expect if this was the Earth model. Okay, other parts of the old Earth, like let's say India and the Himalayas and parts of Europe, are mostly above it. So they would fall off in this part. Okay, so the average discrepancy across here is 29 meters below the ellipsoid. 29 meters may not seem like much on a world scale, but it does indeed make a difference. Okay, how does this translate into mapping? Well, when we measure heights, and one of the things we like to measure for every position on the Earth's surface is its height. One thing we can measure is, say, height above mean sea level. Well, mean sea level was marked on many maps for many, many years, but it's completely arbitrary. You've probably heard that sea level is rising. Well, you think it's risen a lot in this century, just think how much it's risen since, say, the Pleistocene, when it was like 300 meters below where it currently is. So sea level is not a constant level. If we're going to talk about absolute measurements of what's called a reference framework, the three-dimensional form against which we're going to measure the Earth, we need something fixed. It doesn't change over time. So we call this a datum. A datum literally means a one point. It's a one reference point. Now, before we understood that we could actually map the Earth like this and fix this point to an actual point with a great deal of precision, each country on Earth had already started its mapping programs. So here in the United States, mapping began out in the West Coast in the colonial era. In the 18th century, much of the east coast of the country was already mapped in some detail. In the early days of the nation, it was only much later that mapping started moving out further west, although the coastlines had been mapped reasonably well. So once we assume an ellipsoid, we end up with a base elevation for mapping. We call this the datum. And in the 1920s, the mapping of the United States was expanding very rapidly, and there was a need for more and more accuracy. So they figured we'd better have some kind of central reference point to give it a fixed elevation, and we'd measure all other elevations from that point. So they chose one place. It's this one right here. This guy's got his foot on it. It's a rock. Hello? I don't think there's anything behind it. Oh no, they're working on that room, aren't they? I thought I was being spoken to here. So we have a single point. That's kind of weird. Over the course of my career, I've been interrupted by a lot of weird things. I remember once being in Cairo, being interrupted by a donkey outside the classroom. Never had anybody rap on the wall like that. Okay, there's a single point. It's in a place called Meade's Ranch in Kansas. And I love going to famous geographical locations. You can't go to this one. It's on private land. You'd have to have special permission to go to it. But it wasn't always. So they decided that this was going to be a place where they would fix it on the Earth. There it is. It says Meade's Ranch reference point. And they set the elevation there. They calculated the ellipsoidal variation value for that height, and they fixed that height. And they said, this is the datum. This location, this height, is the reference for all mapping of the United States from now on. They call it the North American datum of 1927. So NAD 27 means that the maps were fixed according to Meade's Ranch as the 0 point. Okay. It makes a difference. It makes a big difference. Okay. This is a picture of me. As I say, I love to go to these places. I'm sitting on the steps of the State House in Denver, Colorado, which is the Denver state capital. Not only the largest city, it's also the state capital. It's not often the case in many cities. And I'm sitting on the step that says 1 mile above sea level. They call it the mile-high city because elevation 5280, 5,280 feet, is actually right there by the state capitol. And here is another marker. And that one's actually polished. You can't even read it. It's been polished for so long that all the words on it have gone. And I'm pointing to this one, which is a little further away. Okay, there's the polished one up there. So which is the real mile high? Well, obviously it depends on datums. Okay, so heights are going to be determined on the landscape by what I assume is my Earth model and how I measure it. Here's the actual story. You can see all three now. 1, 2, 3. 3 markers. The first was installed in 1909. It was on the 15th step, but it was stolen almost continuously for several years. That's why they decided in 1947 to engrave 1 mile above sea level on the step. Nobody was inspired enough to steal a granite step, I guess. So the second marker was done by Colorado State University engineering students. They resurveyed the elevation and decided it should be on the 18th step. That's this one. So that's been there since '69. Somebody, I'm sure it's their duty to come out and polish it every day. Well, in polishing it, they managed to obscure it completely. You can't read it anymore. So then in 2003, which actually reflects an important moment because it's the resurveying of the entire country on a new datum, an Earth-centered datum, NAD 83, when they went over to a new ellipsoid. They resurveyed it, and there's the new marker, that one right there. It's on the 13th step. So there's the location. There's me standing up there, where it actually is. If you ever go there, unless it's raining, there's almost always somebody taking a photograph of those markers. So this means that datums change, right? But when a datum changes, we change our entire reference model. It not only changes our height, it also changes our position. Now, I'll give you an illustration of why that happens in a minute, but let's think of the consequences first. So here's a very famous location. In 1884, we decided to standardize the measurement of longitude so that the 0 reference point was the center of the transit instrument at the Royal Observatory in Greenwich, which is just outside London. That is the Royal Observatory in Greenwich. Actually, this is the building. This and this one are the two key buildings where the instrument was. It was a big instrument for measuring the stars, and measuring transits of the stars, as they're called. And that basically set the prime meridian. The 1884 conference, which was actually held in Washington, D.C. at the State Department, was an agreement among some 26 countries that they were all going to use that one standardized reference point, although the United States kind of held out on its maps until about 1920. France still holds out against it, although nominally they also agree. But when we actually take the map, and here I've zoomed in on OpenStreetMap, which we'll talk more about as we get on in the class. If I zoom in and say bring up the latitude-longitude line, so here's the Greenwich meridian, 0 longitude. Well, here's the observatory. It's over here. It's about 104, 105 meters between those two locations. So what's going wrong here? Did somebody get it wrong? When the first person who ever noticed this on Google, by the way, made a whole series of posts that Google had got the prime meridian wrong on Google Earth, and this was picked up by newspaper stories and so on. Well, of course, WGS 84, the standard which we usually use for measurements and we use with the Global Positioning System, is an Earth-centered datum based on the center of the Earth. And when we recast that back to Greenwich from the center of the Earth on the correct 0 degree longitude, we come up with a new position, a new location. In fact, that little path there, and pretty much where that guy's standing near that bench, ends up being exactly where the prime meridian is in Greenwich, not the old Greenwich meridian. We're talking about not just out here, it's way out here beyond those trees. Near that little tree, in fact, is where the actual meridian passes through. So not only does height change as we change datum, we also change position. Certainly change our longitude, we also change our latitude. And that takes a little bit to understand unless we see what's going on here. Okay. So far I've introduced all of these different models of the Earth's size and shape. So we can have an Earth-centered ellipse. Okay, that's like WGS 84. That's an ellipsoid. We can have an Earth-centered sphere. So Egypt, for example, uses a sphere for its mapping purposes. We can have a datum-based ellipsoid. In other words, like, say, mapping in the United States after 1927, when we chose a point in Meade's Ranch as the basis. That gives us a datum, but it's shifted off of the actual Earth center. Or we could actually have the geoid, the precise position for measurement. Okay? Any one of those models could be the model onto which we're snapping observations about the real world. So let's take this particular point on a hill. This happens to be on the border between in West Virginia, near Harper's Ferry, but it doesn't matter, it doesn't make any difference. So if we actually have a location, which of those references we measure to changes our height, okay? But if we project backwards out for any given latitude and longitude, which point we project to on the Earth's surface is a different location. It can be different east-west, it can be different north-south. Okay? So when the United States, during the mid to late 1980s, decided that it was going to abandon the old NAD 27 and convert all the maps, that's 47,000 maps of the United States, over to NAD 83, an Earth-centered reference ellipsoid, it involved moving things by different amounts. The Washington Monument moved, I think it was 11 meters east and 83 meters north. Everybody freaked out about that. They thought they'd actually moved the Washington Monument. Okay? So the good news is that pretty much everybody in the world standardized on what to use as the reference ellipsoid based on this WGS 84, the World Geodetic System of 1984. Now, why standardize on this one? It was about the time they were developing the global positioning system. The ability to use a handheld device to actually measure these locations. They had to pick somewhere. They had to pick one reference ellipsoid and store all those parameters into the system, and they chose this one. Just out of interest, we describe an ellipsoid by what are called the semi-major and the semi-minor axes. Those are kind of like the radii. Okay, so they're shortest at top and bottom, they're longest left to right, but they have a different value in between. We talk about the flattening of the ellipsoid, and that's the 1 minus the ratio of the shorter to the longer length. So this is going to be less than 1. This is going to be flattening is going to be a very small number. Actual values, here they are. You'll notice that A looks suspiciously accurate. 6,378,137.0. Okay, well, obviously they wanted to set one of the two numbers to an integer because that would make the calculation much faster. Okay, so rather than having super precise accurate measurements of both measurements, they set one to an integer and made the other one a floating point value. So it's 6,356,000. That's considerably less. Notice 752.3, and believe it or not, the next decimal places are classified top secret because you can work out orbital geometry and spacecraft and spy satellites and stuff if you know it. So that gives us F, or the degree of flattening, about 1 over 298.257. Okay, so we're about 1 in 300 off of a perfect sphere, pushed down at the poles. That's our Earth shape. Okay, and of course there are more exact data. These numbers, by the way, have now been taken over by something called the International Terrestrial Reference Frame. The international body, the equivalent of the Metric Standards Organization for the Earth and its rotational system, is administered by a group in Paris called the International Earth Rotation Service. I just love that name. Call them up. Yeah, I'd like the Earth rotated one more time, please. But one of the things they do is they maintain all the constants, and since the GPS era, they've been putting together all of the accurate, precise information about locations on the Earth's surface and continuously refining this ellipsoid. So they now have their own International Terrestrial Reference Frame ellipsoid, which is very similar to WGS 84, but decimal places off now for accuracy. So let me wrap up this part of the lecture, which has taken me considerably longer than I thought it would, but that's okay. So for the Earth, the sphere is not bad if we're going to take a model and apply the Earth to it, this scaling transformation to it. It's about 1 in 298th part off. We know from the French measurement that if we go from equator to pole 4 times for the 4 segments, and each one is 10 million meters, and it's 40 million meters around the Earth. That gives us a size estimate, 40,000 kilometers. That in actuality, a much better model is an oblate ellipsoid, and if we do that, we only need to distort it slightly from the sphere to get the best fit, and we can then make that model Earth-centered rather than being arbitrarily based on numbers calculated for any one country. The beauty of that is that Canada's map is going to fit up exactly against the United States map. There's not going to be a 6-foot drop as you cross the border because they're on different mapping systems. And that makes a big difference, and the US has indeed aligned its mapping with Canada and Mexico. Gravity, and therefore down, the direction that something falls if I drop it, what we call down, sort of in the vernacular, actually not only varies in strength but also in direction. So it's not a constant for any position on the Earth's surface, and this goes into shaping what both the position of the Earth's center in an Earth-centered model, but also the force of the gravitational potential, and therefore the best fit geoid that goes along with the Earth. It's often said that if the entire surface of the Earth was water rather than land, and that all of the water could be pulled so that it met the local gravitational minimization of all the constraints, that the surface of that water would fit the geoid on the Earth's surface. So there have been lots of different ellipsoids. Of course, every country that got into mapping chose its own datums and therefore its own ellipsoids, and therefore started its mapping with different assumptions about the Earth's size and shape. This comes into play in quite significant amounts. For example, when Nazi Germany conquered France and Belgium in World War II and was interested in firing rockets at Britain, the so-called V1 and V2 early drones, they put together all the maps and realized that they'd have to take into account the difference between the datums of the mapping of the different countries if they were actually going to hit accurately, because they couldn't hit accurately. So, and then the last thing, and this is very important, if we changed the datum, we also changed not only our height, which is measured with respect to the datum, but also our position on the Earth's surface. What are the consequences of this? Well, they're quite profound. If I've got a map, a digital map, which somebody's created in advance and, say, posted as a data set, and it uses this ellipsoid and this datum, and I've got another map, perhaps even covering the same area, and I want to superimpose the two, if I don't first transform them onto the same geometry, the same scale, the same ellipsoid, the same datum, I've got a problem. Okay? It's like I'm trying to fit two different size geometric objects together when they're not a perfect match. I have to approximate to get them in the right location. All right, so let's go on to the second part of what I wanted to talk about today, and that's map scale. It's a little bit easier to understand, a little bit more intuitive. So map scale, we usually, in cartography, we talk about it in terms of the representative fraction. We usually abbreviate that to RF. And that's simply a ratio. It's the distance, a ratio of distances on the map to the same distance that represents on the ground. Now the distances on the map, usually, generally speaking, are going to be fairly short. Okay? You measure them with a ruler. Distances on the ground are going to be fairly large, so the representative fraction is going to be a tiny fraction. It's going to be 1 over a large number in most cases. In terms of mapping of the Earth, most maps fall between about 1 to 1,000,000 and 1 to 1,000. 1 to 1,000,000, the map, well, think about it, 1 to 1,000,000, a map of the entire Earth, the entire distance around the equator would be 40 meters, right? That's about like from here to, say, the top of Campbell Hall. That's a biggish map, but you can still imagine that that's a map. And there are indeed maps of the Earth at 1 to 1,000,000. By the time we get to 1 to 1,000, that's 1 meter being represented by 1 millimeter, we're really talking about highly detailed maps, floor plans of buildings. Well, certainly we begin to use the word plan rather than map because it's so detailed. Okay, now let me start with this one. When I usually start talking about map scale, most people in GIS say, well, scale doesn't matter anymore, right? Because a computer can do its calculations and rendering at any scale. But in fact, scale does matter. It will always matter. We often say digital maps and web maps are scale-less because we can enlarge and reduce them at any scale that we want. But in fact, I would argue that maps are always highly determined by the scale at which their measurements are taken. Okay, if we're making a detailed measurement of the coastline where we're taking a measurement every meter or so versus we're just scanning a map that has a whole continent outline, those are two very different scales at which we're measuring the coastline. In fact, of course, when we display any map, it has a scale, a specific scale, and we have to know what it is and produce a map that is correct to that scale. So let's say, for example, we have a database that has a point on the coastline every meter. I mean, first of all, that's kind of arbitrary. You know, what does a meter mean when you're sort of walking in the mud in an estuary or something like that? But let's say we could do it. If we were going to draw that map at a very coarse scale, say 1 to 1,000,000, we wouldn't want to draw every single point. There'd be so many points that would just look like one cloudy haze of points rather than a map. Okay, the scale problem is this, is that the amount of information that we can fit on any given map, let's say we have this rectangle in which we can display our map. There it is at that particular very finite size. Let's say that's a window on your computer. We can only cram so much information into that window. Okay? If we tried to put a world map with the name of every single city in the world into that window, it would be illegible. From even sitting in the front of the classroom, you wouldn't be able to see it. So the amount of stuff that we can cram on any particular map depends upon the scale at which we're going to display the map. Now, these days, on computer maps, we kind of assume that we have interactive control. So if you go into Google Earth or Google Maps, we want to see something in detail, we zoom in on it. We want to see less detail, we zoom out. If we do that, we very quickly run into the scale problem. That is that we can quickly get too much information to display. And we solve it using a trick from computer graphics called level of detail. And we're going to do level of detail in a lot more detail as we go on in the quarter. So you could imagine that we could solve the problem in any one of two ways. The first one would be to have one sort of universal map of everything at the most incredibly detailed scale that we have. And then when we have a finite space in which to display it, we simply throw away what we don't want and just take what we do. Okay? That's called a selection problem. And it implies that we have some automated way of doing generalization on the fly. Okay? That's quite an expensive thing to do computationally. A far more reasonable solution is to say, well, you know, if I'm going to use that size window, I'm really only going to be looking at the map you know, maybe I'm going to put the whole planet in that window, in which case I could use, say, 1 to 400 million, or I'm going to zoom in on Goleta, in which case it's going to be 1 to 24,000. So given that I'm going to only display a certain ranges of maps, I'll actually make the map at, let's say, 10 different scales, and then as the user zooms past a particular scale, I'll just go and get the other map and display that one instead of the one that I had. Okay? This multiple representations, as it's called, is the way that this problem's been solved. So if you You go to Google Maps, let's say, and you start playing with that little slider bar. You look at the map, it just appears to get smaller and smaller, and then all of a sudden, boom, features disappear, and it redraws the map looking a little bit different. That's because we've just crossed one of those thresholds from one set of scales into another set of scales. So, yeah.
Is that the same thing as scalable micrographics?
Scalable micrographics. You're going to. Oh, SVG. It has to do with it, but a lot more about that in the lecture coming up on generalization. So I'll punt on that one for now, if you don't mind. So I always say map data have the scale of the source stamped on them, okay, and there's nothing we can do. And one way of proving that is that if we choose any particular scale, let's say we make an image and we choose an equivalent of 1 to 100,000, and then we try and zoom in on that image, well, our pixels have a finite size. And we can take the pixels and make them bigger and bigger and bigger. They're just going to look blockier and blockier as we get more and more detailed. We're not going to see any more detail, so we cut out all the detail below that scale. Generally speaking, maps at coarse scales need fewer features and labels because they have less space to fit them in. So if we're trying to fit the whole world in there and label cities, we might be able to get London and New York in, and that's about it. If we try and do any more, we're out of detail. Maps at too fine a scale are unreadable. So if we tried to draw a map of the world in that rectangle showing a point on the coastline every meter, there are going to be so many points it's just going to look like a mess of dots on the screen and not a line, not a coherent line. Okay, so this is what I call the scale problem that we need to deal with. Here is it illustrated graphically. This is the Farm Mapping Agency's land use map of Santa Barbara County. And then if I zoom in on Isla Vista, I see this. Okay, so here's institutional land represents the campus. Here we see residential land, parkland, and so on. Devereaux out this way. We take this entire polygon; it's simply a blob on here. I can't even make a difference between the lines. Okay, so I've got different levels of scale at which I'm capturing the data and at which I'm viewing the data. Just another quick illustration. I've got another one. I just did this today. I go into Google Maps and go to the same area, and I can see the campus, IV, Devereaux. It's really just represented by a few polygons. We've got major lines in here, like El Colegio is in here, but none of the lines in Isla Vista is here. I just go a couple of clicks down, and bang, all the streets in Isla Vista suddenly appear. Okay, so I'm simply going over to another representation as I've made slight changes in the map scale. Okay, so ideally in terms of scale, if I were going to publish a set of paper maps, not have a digital map, I would probably want to not publish them at 1 to 11,231, which would drive people crazy when they were trying to calculate distances and so on. I'd probably want them to have some kind of rounded number like 1 to 10,000, or 1 to 24,000, or 1 to 250,000, or 1 to 500,000, these kind of increments. I would like the scale to be the same in all directions and at every point on the map. Okay, and that means that 10 meters east-west is the same as 10 meters north-south. In other words, Cartesian geometry applies at every point on the map. Now that involves a set of assumptions we're going to talk about in Tuesday's lecture on map projections. We would like that to be the case, but it's not necessarily the case. We would like the scale to be given to the user in some way that's useful. So we can express it. We can simply give the user the representative fraction. We could perhaps display it in the corner of the map, or we could give them some information about how to measure lengths and distances. And we'd like the reader to be able to interpret the map, that's measure off distances in some way. Okay, I always like to do my baseball stuff, simply because I put so much effort into creating that graphic. Okay, so I very precisely measured off a baseball, and I hope I got it right. I got its circumference at 226 millimeters, and if the Earth's circumference is those 40 million meters that we just talked about, then the representative fraction for a baseball Earth is 1 to 177 million. So that's kind of like an outer reference point, I would argue. I would argue that an Earth the size of a baseball is marginally useful. You know, you might want to take one on a flight between here and Hong Kong or something, because it might be useful a little bit in telling you where you're flying, but it's not going to be very good if you just want to go and buy a pizza in Isla Vista, right? So that's you're the wrong side of the scale equation there. If we know the scale, or if the scale can be calculated, we have some advantages for using maps. So one of the things we do on maps is to calculate ground distances if we have a known scale. Okay, so I can go in on the map and measure a distance. Let's say I want to measure it from this point to this point near northeast. Anybody know where northeast is? I believe it's in Maine, but I may be wrong. I'll have to look it up after class. So I can measure off that distance, and I can have a map distance. If I know the representative fraction, I can get the ground distance, because the representative fraction is the ratio of the ground distance and the map distance. Okay, simple math. I measured it off the map. It was 300 millimeters. The scale of the map is known. It's, say, 1 to 50,000. And then here's my representative fraction is the map distance over the ground distance. So the ground distance is the map distance divided by the representative fraction, which translates to 15 kilometers in this particular instance. The numbers are not important, and they certainly won't be on a midterm. Okay, but we can do it not just digitally, and the latest digital versions allow you to simply click on 2 points and calculate it directly. We can do it in the analog sense. Now, the nice thing about a map is, as one of the quotes in my GIS book is a computer with a bullet through it is an expensive paperweight, but a map with a bullet through it is still a map. Okay, you can still make measurements if you've got a paper map. And one of the tricks for making measurements off of a map is to, if we need to know a distance, is to use what I call the paper strip trick. Okay, so if we've got a strip of paper, and notice that maps, since they're printed on paper, have a convenient paper strip just by tearing the edge off of them, or if you're clever, folding it across. So we can take a paper strip, mark off the 2 points, and now I can move this to a scale if one is marked on the map. And many maps include scales with quite a degree of detail. Some of them are quite elaborate. This is a 1 to 50,000 scale. It's blown right up, so it's not actually 1 to 50,000. But in measuring A to B here, normally I would take the distance, put it on the whole number, in which in this case 3, which ensures that the marginal part falls to the left of the margin here. Okay. So if I moved it to the 4, that would be no good. That would be somewhere in here. But if I move it to the 3, I can say here, this is 3 kilometers plus, and then I can read off, usually the scale on the left-hand side of the 0 point is usually at 1/10 of the grade on this side, so we can read off meters or estimate to perhaps tens or even individual meters on that. So this is 3 point something kilometers. Now the units of scales are very important. The nice thing about the metric system is that all lengths and distances are standardized. We only have 2 standard units of length in the metric system, the millimeter and the meter. Okay? Everything else is based upon those. But that's not the case in history, and it's not the case worldwide. Ironically, it's not even the case in the United States, where, in spite of the fact that we adopted the metric system in the late 1800s and standardized it almost completely 2 or 3 times during the 20th century, we still use this archaic English medieval system of imperial units for some stupid reason.
Blame McDonald's.
Blame McDonald's? Okay, well maybe. Well,
Get rid of their quarter pounder.
there you go. Well, the British, even though they're now almost entirely metric, they still serve beer in pints. They just can't get around that. So here's a nice. I mean, this leads to all sorts of problems of conversion. So here, for example, this is off of a French map of Belle Isle, which is off the French coastline. So we've got a scale in 3/4 of a communal mile. Who knows what the heck that is? And this is a scale in 80 toises. 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 80 toi So if we look back in history at different lengths of measurement, there are thousands of different ones. So a toise was 6 French feet, or 1.949 meters, until 1812. Then it was standardized to be 2 meters between 1812 and January 1840. Toise is still used in Switzerland, but there it's 1.8 meters. Okay, and the common foot, le commun, was the common mile was 4,452 meters. So the bottom line here is that you have to be very careful with your units. Now, you've probably heard the famous story of the NASA shot at Mars or whatever it was that failed because somebody used the wrong units when they did the gravitational calculations. It still happens. Now, this is a good argument for standardization of units. But the bottom line is be very, very careful. You download a digital map, you pop it up and you line it up and you think everything looks great, but everything's too small. Maybe it's in feet instead of meters. You need to be aware of these differences because they can be quite subtle and very important. Okay? We often talk about small scale and large scales in cartography. I don't use those terms because they are completely arbitrary, because the word scale is also used in the English language and it means the exact opposite of what it means in cartography. Okay? So when we say large scale in English, we mean the whole world, right? It's large scale. A large scale in cartography means a little tiny piece of the earth in a lot of detail. Okay, so I prefer to say coarse scale and fine scales, or detailed scales, because that's a lot more meaningful. Here are some examples. And remember, these are blown up, so they're not the actual scales, they're not the actual sizes. But 1/94 million, we can see the entire lower 48 states on this map. If we go to 1/37 million, we're looking at a region. 1/16 million, we're looking at part of a region here, only 2 states. We go to 1/1.3 million, we're looking at a metropolitan area. We go down to the 1/1 million coverage for Southern California goes all the way from San Diego up to include parts of LA. It's a big chunk of real estate. When we start to go below that, when we reach detailed scales like say 1/24,000, we need 2 sheets for Santa Barbara and Goleta to cover them both. When we get to very detailed scales, like say 1/10,000, 1/5,000, we're really going to only be able to cover areas like the whole of the campus on a single map. Okay, so the scale does make a big difference. It's an important difference.
Fine scale would be the more detailed.
Fine scale to me means it includes a lot more detail. Coarse means it's like showing the whole continent or showing the whole Earth. Well, it's pretty much the same thing as I just showed you, but this is last year's slide. The same thing. We zoom in, we're seeing more detail. So here we're seeing features labeled like streets that are not even shown on this map, and we're getting content like street names that are not on this map either. So it's not just the size at which things are going to be drawn, but it's also what we can label and what we can feature. Okay. So in summary, the Earth model itself is the first important base for mapping. We just saw that. Once the datum and ellipsoid is chosen, we can apply the scale transformation, and we end up with a globe. Converting between datum and datum involves going back to the Earth's centered transformation and then retransforming it. So if we've got 2 maps, equivalent globes, but they're on different datums, and perhaps that's just the same country mapped by the same agency at different times, we're still going to need to transform them to get them into the right geometry. And then scale not only affects the size of the content, but the cartographic content, what we can put in there itself, and then also how we tile the landscape. So at 1/24,000, the entire country sits, of the United States and Alaska, well, we don't have the Alaska at 1/24,000, we've got 40,000 quadrangle maps. Far fewer than that, maybe 5,000 at 1/100,000, way fewer than that, maybe a few hundred at 1/250,000, and very few at 1/1,000,000. So as the content, the degree of tiling, the number of seams between maps expands very quickly as we go into more and more detailed scales. Okay, so we've covered the first 2 topics, geodesy and scale. Next Tuesday we'll start talking about projections. All right, see you then.